Everybody, please sit down. We're going to have Jennifer Evans with Clickfox. And again, please support our sponsor after the presentation. Please join us in Chicago. Thank you.
Hi, my name is Jennifer Evans, and I'm very new to public speaking. And so today's presentation is going to be about decision trees, random forest, and using the open source tool R. So I thought it was very important to have some type of context as to why we need to be using these algorithms to begin with, and completely overscope the presentation. You're welcome to text questions to my Twitter account, and you can text them, especially for the remote viewers, and I'll go ahead and answer them, maybe not during the talk today, but as soon as I get a chance to make sure those answers get back to you. All the R code is hosted on our Clickfox site, so you can not have to copy and paste code with the number lines. No. So it's all hosted there. It has some additional stuff, some other R packages that I've used, some other decision trees that I've built, and some examples. So if you're interested in all that, please feel free to use it. All the code is not mine. I didn't write everything. Some of it's been borrowed from different locations. My colleague has written a lot of it. But you're welcome to use it to play around with and to familiarize yourself with R. So in this hour-long talk, I'm not going to be able to teach you R, but I'm sure going to try. So the outline, so I have a brief overview of what data science is, what we do at Clickfox, what our team does, and then we're going to go into some detail about data preparation and why that's important. And really, you get data from somewhere. You have to do something with it. And you have to think about what you're feeding into the algorithm. You really don't just collect as much information as possible and then expect your algorithm to run and spit out something useful. So we're going to talk about decision trees, specifically the R implementation of the classification and regression trees, and knowing your algorithm. And what I mean by this is read the documentation. Because nobody enjoys writing documentation. What they wrote, they felt was imperative for you to know to use the package. And it talks about the parameters. And that's extremely useful. And sometimes your algorithm will do stuff you didn't realize it could do. So reading the documentation is there because it's the bare minimum that people had to include with their code. So after you build your model, well, you have to measure it somehow. So we have some evaluation metrics. And then Kaggle random forest. I know a lot of the interest in random forest is because of Kaggle competitions. And one thing about them is everyone's given the same data set and runs random forest. And so how do you really win a competition if everyone's doing the same thing? So I'm going to talk a little bit about some methodology you can do that to give yourself maybe a slight advantage. And once again, we're going to go back to data prep and why that's important. Some visualization and some recommended reading. So data science, a brief overview. I mean brief. It's a meticulous process of iterative testing, proving, revising, retesting, resolving, redoing, programming, because you got smart and thought automate, debugging, recoding, debugging, tracing, more debugging, documenting. Maybe you should have started here. Analyzing results, some tweaking, some researching, some hacking, and start over. And data science at Clickfox, so our team has kind of three, I'm determined to drink this water here. We have three kind of areas of focus. We're building a software platform to really enable other people, especially businesses, to do their own analytics. And so one of the things we specialize in, we take data from disparate sources, such as your web data, your IVR data, and your retail data. We tie it together and give you a traversal string. So now we have this very complex time series data. And a lot of it are unique traversal strings. Well, we're trying to add analytics onto this data type. And we have client-specific engagements. So we have a client who wants to do analytics, such as a term model. That's outside the capabilities of our product. A lot of times their team will get engaged into that. And then really we want to focus on enabling everyone to be more capable of making data-driven decisions. And I got a clicker, but I'm still gonna stand here right on my computer and press the button. So the problem today that we're going to answer is, will it rain tomorrow? And so we think about this problem, this is our business problem, for the sake of this talk. Well, what kind of information do you need to predict the rain? And so you start thinking about, well, it might be useful to know how much sunshine we have, how much evaporation we have, how much rainfall we had today, what the humidity levels are, maybe the maximum temperatures. And so these are kind of some of the variables we might be interested in to determine whether or not it's going to rain tomorrow. And so really the first step is you have your question and you think about what you need to answer, or what type of information is of interest. And so we start doing the data preparation, we start going and collecting data from different places. And it oftentimes comes from different places in different forms, and you might have data for humidity that's been measured every 5 minutes, but just one high temperature for the day. And so if you're going to use data from a day, you're going to need to get it to a form that's usable. Well, when you get your raw data, it oftentimes looks like something incomprehensible. It doesn't necessarily fit together. You don't necessarily know what you have, and so you have to spend a lot of time looking at each piece of it to put it together and to get a nice uniform whole. So we begin creating our analytic data set. And so we start taking those pieces of data. Maybe you have something in a database, maybe you have something with this different ASCII code encryption, and you start trying to find a way to tie it all together. In my company, we're a little bit lucky, where we have some very talented teams that take the raw flat files and put them into a database. So we have data analysts, data architects, and information architects, which put our data from the flat files into a nice uniform structure into the database. So on to data munging and data creation. And so this is when you start thinking about the information you have and ways you can combine it to create new information. And it's important to think about, what else do you want the algorithm to see? What else could be valuable and important? And so if you're trying to do predictions on car sales, if you could even split it apart and say, well, these cars from this region are more likely to have rust. And so that's an additional variable you can start adding. And thinking about that. So a lot of it's art, a lot of it's creativity, a lot of it's kind of domain knowledge, where you think about what you have and what else you can get from it. And then you start checking data quality, make sure it's been preserved, make sure you haven't done something math magical. So this picture, it's not so bad. It turns out that banging your head against the wall burns 100 calories an hour. And so we start putting together all our data that we've collected. And you have types of bad data. There's missing data, which is different than just empty, or you have different types of missing data. You have inaccurate data. And especially depending on where you're getting your data from and what the context of it is, because people lie on surveys. If you're looking at user ratings, maybe people are ranking 1 star and saying, stay away from my favorite restaurant. Poor interpretation and polluted. So sometimes too much data, if you have too much data for what question you're actually trying to answer, it can create additional problems that you wouldn't have otherwise had to deal with. But a lot can go wrong in your data collection process, the data storage process, and the data analysis process. And so one example I have is I was at the mall with my nephew, and we were approached by somebody who was doing a survey, and so she was looking for somebody who's 6 years old to watch a trailer to a movie and answer some basic questions about it. And we started off with that. Here's my nephew's 5. She's looking for a 6-year-old. And so he agreed to go ahead and watch the trailer and answer her questions. And so it wasn't too bad to begin with. She had some easy questions like, is this interesting? Is this a movie you'd want to see? And these are questions he is capable of answering. But some of the questions were a little complex for even a 5 or 6-year-old. does Hiccup, who's the main character, does he seem intimidating? Is this movie enthralling? Right, and so my nephew would sit there and just kind of like stare and start guessing, or ask for a translation. And so sometimes we'd give him a translation, but sometimes we'd give him the opposite translation. And so then he'd be answering the opposite question, which we'd go ahead and enter what he said. And so there's a whole lot of just mix-up with this survey. That the data just got messed up right at the very beginning. And so if you're getting this data as an analyst or a scientist trying to extract information from it, maybe about what things to change to make 6-year-olds more interested in, you might want to think about tossing out all data from 6-year-olds because maybe they're 5-year-olds. Maybe it's just a surveyist. Maybe it's the fact that 6-year-olds check out after 20 questions, and so the first 20 are the only relevant answers to begin with, or re-scoping the questions, and really kind of maybe rethinking the way you're handling the survey, and say maybe just 20 questions, maybe simple words where they can understand what they're doing. So another example is some troops that were, some of our military that were overseas, and there was a group of people that were congregating nearby. And so, of course, they start preparing for attack and planning their defensive maneuvers and doing analysis on the way that this group was forming and trying to establish how to best defend from an attack. And just flooded the radio and the information stream with data, with information. But it was unnecessary because they overlooked the fact that it was women and children who were amassing, and there was no threat. It was just simply civilians that were collecting nearby. And so that's what I mean, in that depending on what you're looking for, you might just have too much information, you'll miss what's important. So another thing about domain knowledge and how data can be messed up is a manufacturing plant was interested in the variance of some of their equipment. So they're building, it was like a bolt or a screw or something. And they wanted to know the variation between pieces. And so they're measuring it. And they had some very, very, very fine precision measuring equipment. But when you looked at the data, when you plotted it out, you would see that you'd have outliers much, in excess of what you'd expect from random variation. And so looking at it in more detail, you realize that the measuring equipment is periodically bumped by employees. And so it's just little things that can happen all along the way that you want to pay attention to. And so it's really important to get very close to your data, where it comes from, and how it gets to you. And my favorite example is that some chemical engineers, and so we all know the chemists, and I'm sure we've all taken some chemistry-filled courses in college. And so there's very strict guidelines, there's very strict procedure. You do your lab, you write down your experiment and your data, you have people check your data, and there's just a very, very well-structured process to make sure everything's accurate. Well, when you go to put it in the database, it became a disaster. That they had a database that evolved over time, that they didn't have really strong restrictions on how you could input fields or information, and flat files. And so if you want to do analytics on a large scale, you are faced with this complete mess to tie everything back together. This example is actually from Richard Cotton, who's an excellent R programmer and has some really good information about writing pretty code. Other things that can go wrong. Right, so you get all your data down, you handle all your bad data, and you have a parrot hanging out on your computer. Don't let the bird help you write code. And we're not going to talk about all the things that we can do to really screw things up. So you get all your data together, and there's still no guarantee that the data you have can answer the question that you're asking. So another thing to pay attention to. So we've collected data to answer the question, since we knew what the question was before we went and got a bunch of data about whether or not it's going to rain tomorrow. But sometimes you're just handed a pile of data and told to figure something out, and really it's your responsibility to say, well, well, no, I need to know what you're looking for. Because otherwise, you can find something fascinating, and just really, really great, and they're not interested in it, they already know it, they can't act on it. And so you really want to make sure that you know what the business question is before you start doing an analytics project. So you get your final analytic data set, nice flat file, you got your variables, you got your rows, it's beautiful. And we're going to answer whether or not it's going to rain tomorrow. So this is what a variable list looks like. We have date, location, some wind speeds. We've collapsed some data, so we don't have cloud temperatures all across the day. We have one instance at 9 a.m., one instance at 3 p.m. Whether or not it rains today. And so we don't have a very extensive data list. We could certainly have more variables. We could have more days. We could have more cases. But this is where we're going to start. Right, and so when you have a question, you have a project, well, you start somewhere, and then you move from there, and then you kind of come back and iterate, maybe add a few more variables, build a few more trees. And so the data set we're using comes from the base R package. It's the weather data set. This is what the first few rows look like. You can take a look at it. And you start thinking about, well, so we got our variables. These are reasonable variables to have. Are the data, do the variables have data values that are reasonable for those variable names to have? And also kind of one of the things when you do in your data prep is you want to have well-named variable names. And sometimes you don't think that that's the most important thing to focus on, but a couple weeks down the road, you're like, well, where did this variable come from? Because you have 7 names appended together and some lookup table and 100 variables. It becomes very cumbersome to start backtracking. So well-named variables, reasonable values. I don't see anything that looks suspicious right away. So dates are in the date field. Measurement fields have numeric values, and counts of occurrences greater than 0. That looks good. Once again, kind of with those questions in mind, check again. So sunshine has value. I don't actually know what sunshine's measurement is measured in. It's just some number. I'm accepting it. This is how the data set came. But that's the thing that you want to know. How did you measure sunshine? Another thing to notice is that we have both numeric and categorical variables. So a few algorithms that throws out kind of right away. Like regression models. I mean, that's going to be very difficult to try to use all your variables, but straighten them out. You're going to have to do some fancy computational transformations. And so R has a nice summary function where you can check the max, the min, the median, the first quarter or quartile, and it just kind of does some basic aggregation for you on all the variables to help you look at it and get a feel for your distributions. And once again, we're looking at the data to make sure that it makes sense and to make sure that it can answer the question, will it rain tomorrow? And start plotting them, start looking at them, look at the distributions of them, look at how they relate to each other. Once again, R has some really great functions to do this. And so pairs, give some variables, give your data set, title it, and you can plot your variables against each other. And you can look at them and check, well, do they have some linear relationship? Do they have some other relationship? I mean, it's interesting how people plots. And this is nice too, if you notice how the open circles, so you can see where there's denser areas, because they start to build on top of each other, so they have a level of transparency. And that's something you want to kind of keep in mind with your visualizations, is whether or not your plots and graphs are actually readable or understandable, or when you look at them, if they maintain the value that they're trying to portray. So a few more variables. We plotted, and then rain tomorrow, that's the variable that we're interested in. And so this is our label training set. So we have the number of dates, and whether or not it rains tomorrow on those rows with those variables. So some more plots. I didn't plot all of them. I thought about it. I did. And I'm actually really glad that chair's here, so you can't see how many slides I have in this presentation. Strategic placement. So you can do a histogram or kernel density estimates of your variables. This is the R code for it. And so a lot of what I have is I have the R code and then I have some other stuff. If you're interested in the R code, I encourage you to copy it and run it on your own and kind of start seeing what it does and doesn't do. Use different data sets, use different packages. So histograms. So sometimes when you're just first looking at your data and your variables, aren't the most intuitive things. It's kind of hard to pick how many breaks you want it to have, and whether or not that's an appealing color of blue if it complements your header very well. We're not going to talk about how much time I spent on that graph. Or you can do kernel density estimates of all your variables and start looking at the distributions. And start just thinking about it, about the data you have and whether or not it's reasonable. And we spend about 80% of our time here doing data prep. We don't run fancy algorithms all the time. We don't do fancy visualizations. We sit there, the database, the data, and we try to get a feel for it. And so some of this might have been excessive. I went ahead and plotted all the variables and put them into LaTeX because I was having fun doing it. And then I went ahead and left them there. So this one is rainfall, evaporation, sunshine, wind speed. These are the kernel density estimates again. Humidity, minimum temperature, humidity again later in the day, pressure later in the day, cloud coverage, or cloud at 9 a.m. And just looking at the distributions of all these variables, I kind of thought was fascinating, so I wanted to share it, whether or not anyone else was as interested as I was. And then another thing that you can find out when you start looking at each variable individually is whether or not you have missing values, or if you have outliers, or if you have stuff that once again looks suspicious. There's nothing worse than getting halfway through your analytics project to realize something very, very obvious that you should have found early on is giving you just epic problems. So we checked all our variables. And we found that we have some missing data in some of our variables, and now we can make decisions on what we want to do with that. If we want to impute it with the mean, or if we want to use something a little more intelligent, if we want to give it kind of its place among the distribution that we just plotted. And we did our random simple checks. Another thing with time-bound data, so we have a lot of it where I work, is we get data for a day, but it kind of leaks over into the following day by a few hours. And so that's just something to be aware of and make sure that that's being handled. The data for this data set, since we have day to day, it's been well partitioned, but another thing that we went ahead and checked. So we have our data, we've checked our data, we can get on to algorithms, which is just a whole other topic. We know that we're going to use cart decision trees and random forests. We know that this is a representation of a real world phenomena, that it's not everything there is to know. It's just a representation to help us make decisions or do a basic prediction. So there's decision tree and random forest. And random forest is basically an ensemble of decision trees. Very thorough explanation. And so I'll give you an example. If I was very indecisive, let's say, and I wanted to watch a movie, and I asked one of my friends, Willow, whether or not she thought I would like this movie. And so she's going to ask me some questions about movies that I have watched, and whether or not I have and have not liked them. And so she's going to ask me questions like, well, is Johnny Depp in this movie? Is it a romantic movie? And is it a scary movie? And so I'm going to kind of give her a labeled training set of movies that I like and don't like, and some of the variables that go along with them, and whether or not that's present. And so when she asks me, or when I ask her whether or not I'm going to like a movie, and she's going to play like a 20-question game with me, And depending on whether I say yes or no, so she's going to split on that variable and effectively be a decision tree for me. So she does not generalize well. She can basically tell me specific things about the specific movies that I gave her in the label training set. So I'm going to ask a few more friends. And I don't want all my friends, because I'm going to assume that they're very intelligent beings and make the same decision based off of the same information that I give. So if I give two people the same information, they'll come to the same conclusion. So I'm going to give everyone slightly different information. So I'll give Willow some subset of the movies I like and dislike, and then somebody else some other subset. And I'm going to split the data into to give different data to different friends. So I'm going to ask some random friends. I'm going to ask Hartman and Professor Cat. And all together, they're going to be an ensemble of decision trees. And so I'm going to take what they say and I'm going to put it all together and average it out, whether or not, how they vote. They don't all have the same information because I've given them a subset of the data. And they're going to split on different variables. And so when you look at a decision tree, you give it the whole data set. You feed the algorithm your whole data set. You give it all the variables, and it looks at every row, and then it thinks about it, and it wants to maximize the purity into the two tile nodes. And so what that means is, with the movie example, it's going to maybe take it and it's going to split everything into scary movies and not scary movies, and then that's it. There's no going back. And so you basically cast your first stone. And there's no guarantee that that first split was the best one. It only happens at that level. And so everything down the street, it doesn't really think about all the rest of the data available. And so one thing about random forest is you don't give it everything. You give it some subset, and you only let it split on some subset of the variables. And you do a whole lot of trees, and you let them get as big as they want to. You just let the trees grow, and then you put them all together and you let them vote. And so you individually have just a whole group of very, very bad predictors, which you put together, and they start to boost each other's performance as they average out. And so in some ways, it kind of minimizes that cast the first stone effect, because you can have a different subset of variables to split on for each different tree, and so it starts to average out together. And it also avoids the problem of overfitting pretty well, once again, because of that aggregate. And so when you look at each individual tree, they're just completely wrong. And so you don't really know where they got, you don't have any idea how they got to be that way, because it's not very intuitive, it doesn't make sense. And it's very, very difficult to pick apart the random forest and say, well, which trees were the actual good predictors? Because they all start kind of canceling each other out, and you have a few trees that are good, a few trees that actually discovered the structure of your data. But they're very, very difficult to find. And there are ways to try to do that. But once again, it's very difficult, it's not intuitive. And so the decision tree, it's kind of easy to see and easy to follow, but it's very, very limited, and it can be, it doesn't generalize well, it can be overfit pretty easily. But your friends are a bootstrapped aggregated forest. And what that means is because of the sampling method. So as we do the random sampling of your data set, and you give some portion of it to each tree to build, or to each algorithm to build a tree, that's how we get this aggregated bootstrap method. And when we talked a little bit about that, how we only let split on a subset of the variables. And so if I have a data set with 25 variables, I'm going to let it sample about 5. Maybe 4, maybe 6, you're going to go ahead and try that out and do your evaluation metric and see how it comes out. Every data set's different, and you want to play around with it, you want to play around with your parameters. And another thing is the sampling method. And so random forest does, by default, the sampling with replacement. What that means is if you have a 1,000-row data set, and you sample one row, put it back, sample a row, put it back, sample a row, put it back, which is computationally intensive. And then it gets rid of any duplicates that it may have sampled 2 or 3 or 4 times. And it averages out to about 63%. If you build infinite data sets, that's kind of the limited approaches, which is also time consuming. And so once again, we add together all our forests, we get something accurate. Or all our trees in our forest, we get something somewhat accurate. I'll let you guys read this. I actually brought 2 water bottles. It's like the challenge of the day, is to stay adequately hydrated so you can speak properly. Thank you. So we thought we get a consensus. Too bad all voting methods didn't work this way, where people have no idea what's going on, kind of cancel out, and what you're left with is something accurate. So decision trees, and all. There are a lot of tree algorithm choices in R. Here's only a couple of them. We're going to look at the top one. But there are a lot. And so some of that code that I have on the Clickfox website has some examples of running some of these other trees and building them. I especially like the evolutionary algorithm concept because kind of what we talked about earlier is how it has that first split to maximize the purity of the 2 trillion nodes. The evolutionary algorithms kind of start from the bottom and start to build their way up using some mutation. Thank you very much. Some rules. So basically they have some rules, some like combination, mutation, and ways to start building back up, and specifications you have to meet to become a parent node. There are a lot of forest algorithms. So once again, so the forest is just an ensemble of decision trees. You can use different trees, you can use different types of trees, you can use plenty of other things that are not trees at all, and tie them all together and get an aggregate. Here are some implementations in R. The survival forest is also by Leo Greiner. And so his work is absolutely worth reading. And he has another concept of the born-again decision tree, which kind of helps you start thinking about, well, how are you going to more effectively communicate around the forest to your business? So some other ensemble methods and useful packages. And some of these other ones too, the example code. So once again, as I overscope this presentation completely, like I properly overscoped it, a lot of this code kind of got put onto the site, so you can take a look at it later if you're interested. Some more of the stuff has gone into detail, and since it was the first iteration, I haven't gotten around to properly documenting a lot of it. And so, some useful commands in R: the summary, the head, tail, the structure, list the functions that are in a package. So as you load your libraries, and you kind of want to know what's where or where it comes from, then sometimes stuff gets double named, and so you want to know where it is. And then if anyone's interested how I got some of the plots into this presentation, it's that bottom code there. So knowing your algorithm, read your documentation. This is how the cart. I think the default is the Gini index. This is how it's the criterion to make it splits. There's some other ones that are commonly used. Once again, so just split at each node, maximize the purity of the children. And not all the tree algorithms are like this either. And this one specifically, this is how this one works. So some example code in R. These are the libraries. I didn't get through all these ones in the presentation, but these are all the ones that I used in the example code on the website. And so some basic data prep. We have the weather data. We set the target variable to rain tomorrow because that's our variable of interest. And our variables, we're going to ignore date, location, and risk. So we set the difference there. And so this is a sampling for the training and test set, where I take the data set, the weather data, and we're going to sample 70% of it for the training, and the rest of it, 30% for the test set. And what I'm doing here is I'm not actually rebuilding any data sets. I'm sampling the rows from the data set that I have. And so 70% of those row numbers are assigned to my variable train, and then the rest are assigned to variable test. And so when you see my function calls, you're going to see me call the row numbers and then the set. It's okay to split the data like this in this specific case because the variable of interest is common. If you have something that occurs very infrequently, such as churn, maybe 1% of the time, you want to split your data up a little more intelligently so you can maximize that variable in your training set so that your algorithm can see it. And that's it. That's all it is to build a tree, is the formula that we set earlier, and the data is, and as you can see, that's row numbers and then the variables and the DS data set. So I'm subsetting both the rows and the variables. This is how it handles the NAs, which we talked about. There were some. I actually built another data set which is called DS complete, where I just removed those rows. So to run the random forest, you can use the default action, but it takes a long time to run. And so a lot of this is stuff that takes a long time. And so how do you make it run faster, especially if you're looking to put something in production or if you have large data sets? So print and summary commands. Here is your tree.
Could you explain what surrogate splits are?
Yeah, so if you have a variable that's missing, so we have an example where sunshine is missing, and so if the decision tree wants to split on sunshine, it says, well, this is the most important variable, so we need to split here, but for that row it's missing, it'll say, well, what's the next best alternative? And so it happens when there's missing data. So this is what the tree looks like. So we have the root node, it splits on humidity, pressure, and sunshine. This is a summary of the model. It bleeds down off the page a little bit. This is once again just kind of give an example of what the output looks like. It gives you some metrics about variable importance, saying that humidity, sunshine, pressure, maximum temperature, a little bit about clouds. And so when you start thinking about, well, if you're going to run a few more iterations, maybe putting in pressure at noon and pressure in the evening, and maybe adding a few more variables like that, where you sampled those instances throughout the day if that's available. This is the complexity parameter. Once again, this is just for the basic one decision tree. To keep it from overfitting, you want to look at how complex is this tree. So basic plot, and then you can see how it's split at humidity, then again at pressure, then again at sunshine. Fancy plot. This is from the Rattle package. And maybe you just want to access the object and build your own plot and tell exactly how you want to look. You can certainly do that. Here's another plot using the, I don't remember exactly where PRP was from. But, so these are just different representations on different ways to plot your one tree.
So do you remember how, roughly how accurate that particular model was on the test set?
Yeah, this one was about, so the one I used for this presentation was resubstitution error rate. And so basically saying how many times did you misclassify, say yes, it's going to rain, well, it wasn't going to rain. And so this was about 80% accurate. This wasn't the most accurate one by any means. The random forest one won out. But with a variable with 4 variables that you split. And so I have another example where we ran that in parallel. So Here I'm setting, so I'm dropping out the, just the whole row that has an any value. And so now I have my train complete and my test complete data set, which don't have any values. And that's going to be just to run the random forest model. And here's an example of pruning the tree. Maybe you don't like the default complexity parameter, because we all just love R code, so there's a lot of it here. So this is correcting the data to run in the random forest. Random forest, it has to be factor or numeric. So I'm setting those variables. They were something else, like integer or something else at the time. The factors cannot have more than 32 levels. And so we've absolutely ran into some problems running the card decision trees and random forest on data that's been too big. And I haven't actually pinpointed the exact breaking point, but there are limitations. You can only feed it so many variables, and some of it might be with the formula call where it can't take more than 255 variables. Some of it could be it's trying to make computations that are outside of its capability to hold. Another thing is memory. It's easy to run out of memory. If you use the servers at your office, run random forest, you're going to have the DevOps teams creating applications called Random Lumberjack that search for user Evans. Application R. Yeah, run your forest in nice mode. So here's an example. So this is just the default random forest call. And you can see, so the reason I set the formula and the data the way that I did is one, so I didn't have to replicate many data sets that I'm trying to hold to memory. But also so that I have a kind of a much more reusable like call for these different algorithms. To give it the formula, you give it the data, you give it your data set. This one we tested the runtime on, and so we were doing some comparisons with changing the sample size, changing the forest size, changing the sampling rate, and playing with a lot of the different parameters to see what's going to run faster, what's going to be more accurate. I'm not going to let you guys watch the screensaver that I created in R, my visualization about how all that changed over time. I didn't get a very positive response from it. So we have to handle the NA values. This is why we looked at all our data at the beginning, so we can kind of start thinking about what we want to do about it if we have stuff that's missing or just plain wrong. I'm going to let you guys read this. This is from Wikipedia, and this is just the bagging and the sampling rate. As we talked about, has a limit. As you sample and sample and sample, it approaches that number at 63.2%. But sampling something, put it back, sampling again, it's computationally intensive. So why not just sample 63.2% of your data to begin with? That's what we did. It runs a lot faster. It's a lot more accurate too. Probably because we couldn't actually exercise that off to infinity. This is what's going to happen. And so we run around the forest with the replace equals false. As you can see there in line 3. The sample size is actually not by default, but I put it in there to show you where you would set your sample size. And so what you can do, actually, you can set a lower sample size and just create more trees. Be just about as accurate and run a little bit faster. Once again, just depending on what you're trying to do, how you're trying to run this, that for the most part seems to work just fine.
Is there a good choice for the number of trees? You've got 500 set here.
That's the default number. Usually we run at least 1,000. If we do a smaller sample size, so if we're doing maybe 20%, we'll probably run maybe 5,000 trees. Usually 5,000 is probably a good number for just about all data sets. And what happens is at some point you reach a limit or like a plateau. So each additional tree won't give you really any improvement. It'll still fluctuate within some level of variance depending on your data set. And so that's going to actually vary depending on your data, but eventually you will we will reach a threshold where more trees does not give better results. It just takes more time.
Thank you.
Is that deterministic, or do you reach a phase where no trees give you more, but then suddenly you get, I mean, sometimes chaos?
I'm not sure I understand the question.
Is there a threshold where adding extra trees gives you a big boost eventually?
I'm
Like it
saying
flattens
that
out.
you add trees and you're not getting any more information, but suddenly, does that say you'll never get more information? Or
Pretty much.
Yeah, I mean, it's rare because it's because of the randomness of the model procedure, you're not gonna run into that problem.
And that's
very
cool.
often.
Oh, yeah. And plus by that time, we were random lumberjack. By that time, we were random lumberjack.
No, but that's a good question, but it's very rare that something like that would happen just because of the nature of the model.
But it could.
I mean, in principle, it could happen, yeah.
So this is your random forest. This is what it looks like when you call print model. This is what it tells you. And it kind of just repeats your function call to you. Tells you your trees. The number of variables tried that you split is 4. Our error rate, which isn't the resubstitution error rate. This is a summary. This is a structure. This goes off the page. This is actually quite a bit of information here. The importance. I think importance is set to true by default, so you don't have to ask it to capture the importance information. I know that there's some stuff that you lose though when you do random forest in parallel. But so this one says min-max temps, rainfall, evaporation, sunshine are most important variables. This is how you run the prediction. And think of your model, give your new data. Here's an example of running in parallel. So we set the number of cores to 4, 500 trees, so 125 trees per core. We have the time there down at the bottom. And so for these small data sets, or this very, very small data set, you don't really see much of a time difference between parallel, not parallel, sample size, and the different parameters, but doing smaller for the M-try, you can see it on line 12. For this one, I have M-try set to 6. The smaller M-try is, the smaller your sample size is, replace equals false, the faster your stuff's going to run. And so if you're building model after model after model, you don't want to wait a day for it to pull itself together. So we have 24 variables that I fed to the model. So approximately the square root of that is going to be the right number to use. 5 was too many, 6 was too many, 4 was the good number in this instance. This is the next model. This is the importance. And then this is the random forest in parallel. As you can see, a lot of them, they give us pretty much the same information. Run the predictions, do confusion matrix. So you can see kind of our accuracy there at 0.8485%. This is for the one in parallel. This is an annoying little thing that sometimes you're going to have to do if you don't do your data prep well, especially so if you're doing the Calvin competitions, you're just running around the forest. A lot of times you're going to get data in the test set that they haven't released to you initially. So you're going to give a training set, you're going to build your model, and then when they give you the test set, you're not going to be able to apply your model because you have new factor levels. So this piece of code is going to help out with that. And so we went through all that work about plotting decision trees and looking at them. So how to draw a random forest. Random forest visualization. So evaluating the model. So evaluation metrics. Like I said, we're going to just use a resubstitution for these examples. Number 6, the root mean squared logarithmic error is the one that's commonly used for the Kaggle competitions. That's in the package metrics. And one more type of tree, the conditional inference tree from the party package. And so I'm going to show the examples of the evaluation metrics on these trees, and then we'll kind of tie it all back together. So this is the plot. So the party package is pretty good, and so I didn't want to not include that as I overscope the presentation. And was thinking about what to include and not include. This is what it looks like when you print it out. Here's kind of the difference. They do have different selection criteria. And so once again, we're talking about how you get that bias at that first split. And so in theory, the C tree is supposed to avoid some of that bias. And so sometimes you give a accuracy, but you get a more descriptive tree. So a significance test instead of the information game. So we're going to prediction, do the confusion matrix. There's another example of doing the error calculation. And so we have a 78% accuracy. So not quite as accurate as our random forest. Still not too bad. It's pretty comparable to our cart decision tree. Do the probabilities the same way. You do the summaries of it, you get the same information. And so these commands kind of use throughout the whole process to just continue looking at your data. Here's a rock curve. Thank you. I'm so chatty, it's not your talking.
I need somebody to do that for me. I'm going to tell Mike he needs to. You're lucky.
I mean, if I, it is water.
That's right, I didn't know I could get water. I was thirsty forever. I kept asking questions.
So here are those plots from the previous slide. Not a rock curves. And once again, so we're just kind of evaluating a model. These are different methods to in the code to use to evaluate it. A lot of times you'll find that you do something the hard way and something's already been implemented. And so all this code actually does what that first line does, where you do the cross-validation. So you basically build 10 trees. So you sample 10 times, build 10 trees, compare it to your test set. So you can have a lot more code to do something. That's what I've always found. So you write something and then you find somebody who wrote it and you do it the easier way. Sort of package. The carrot package, read the documentation, has some useful stuff in there. So glad you guys couldn't see that number at the bottom down there.
It's such a tease. Are we halfway? Are we?
I have no idea.
You have no idea.
This suspense is killing me.
So we have some more. So we have the C4s in package party. And so we look at that. So we have 80% accuracy. We can look at the sensitivities, the specificity numbers down there. This is the best model though, at 96% accuracy. And this is the second random forest model we built. And what happens, so you oftentimes start building a lot of models, you want to kind of keep some version control, some documentation along with it, and kind of try to keep track of where you are. So here, so we're still trying to answer that question, is it going to rain tomorrow? And so the whole process, it's easy to kind of maybe lose sight of what you're initially doing, but here is the data we have for today. This is our temperatures, the rainfall, the evaporation. I, of course, made it up. It rained today, and so we put it into our model. It tells us, yes, it's going to rain. We do probability estimate, gives you the chance of rain. And this is the random forest model. This is our good model. And so our conclusion is yes, it will rain tomorrow. There's a 90% chance of rain, and we're 95% confident that we have a 5% chance of being wrong. Right. So can you do better? Probably. Can you add more variables? Probably. Once again, this model is very limited specifically to the data you gave it. So there might have been hundreds of variables that you're missing out on. And so because of that, maybe this is completely useless. That you just picked all the wrong stuff and missed all the important stuff. And so this is still within the scope of the model you built. Evaluating the business question. So is this a value? Is it understandable? We kind of walked through what things are important about rain tomorrow. We can certainly brainstorm about additional variables to add and iterate, start all over again. And are we answering the question asked if the question is about rain? And remember, an approximate answer to the right problem. John Tukey is a very brilliant man. He has a lot of good, wrote a lot of really great stuff. He's certainly worth reading and looking at as well. So Cabo around the forest. So you get the advantage of creativity, understanding the data modeling and data creation. So you think about it, so you get a nice flat file. And that means that somebody in the office has already spent 80% of their time doing all the data modeling, manipulation, metadata creation for you. So there are things they could have missed. And just think about that process. Well, what has happened up until this point? And the best way to have a good idea is to have lots of ideas. So just try a lot of different things. You know, maybe something's going to work. And so knowing and understanding the process, look for data leaks and holes in the data set. Look for things that are wrong. Look at your variables and look at things that seem to be amiss and distributions that are abnormal. I mean, the data scientists aren't perfect. What?
Understand.
Yeah, we're like very far to the presentation now.
We've done well up to this point.
Version
Have
control.
you noticed any others?
It was just ironic you were on the page.
That is. It's
Yeah,
ironic.
I'm gonna put the spelling error in one pot. Yeah, I was just trying to see if you're still paying
It
attention.
was intentional.
I was like, you know, probably everyone's gonna check out by the end of the presentation. We actually took bets on whether or not I would lose my voice or if people would check out first. So some version control, write notes, keep comments, read the forums. Visualization. Sometimes you really just need a pie chart.
I hate punches.
Here's some recommended reading. Some acknowledgement to Ken McGuire and Robert Bagley, my data science team and the VP of Research and Development. So we have questions. You're welcome to email me your questions. If we don't get a chance to get to them, I'll send them to my Twitter account, the website for the archive, and everyone, thank you very much for bearing with me in my overscoped presentation, but I thought it was very important.
Question.
For drinks, we'll go over to Mr. and get to them live.
I have one question.
All right.
So, random forest seems to return really good results compared to a lot of the other tree models, but you don't get your rules of thumb out of it, like you might with, recursive partitioning or something. So is there something that's like somewhere between random forest performance, but intuitive for a manager to follow up the tree and get rules of thumb?
So one thing, so there's a lot of, kind of work being done around this idea. Random forest is great. It's very accurate. It doesn't tend to overfit. It handles, your numeric and factor variables. It doesn't take a lot of time doing data prep. You don't have to straighten out all your variables. You don't have to make sure all your linearity assumptions are being met. So it's a really great algorithm, but once again, it is hard to explain. And so remanufacturing a data set that you run through your random forest algorithm and building a decision tree on that, so born again decision tree. Once again, it's time consuming and challenging, but not a bad idea, so then you could get your descriptive power as well as your accuracy. But another thing you can do is just do both. Build your decision tree, build your random forest. So this one's to explain, this is your explanatory model, this is your predictive model.
So like, I'm just wondering, like, what makes random, what are the factors that makes you arrive at conclusions of applying a random forest to a particular problem instead of other, like approach, like, for example, using hidden model for doing random forecast, or like some kind of stochastic modeling instead of using random forest.
Random forest is usually a great place to start. And so before you start iterating too much, and you know, maybe if you don't have a very large toolbox of algorithms, random forest is a very good one to use. How do you know to start with it? You don't. But you try it, and you try other ones, and you start to see, well, what's going to work for your data, what type of data do you have. If you have all factored data, maybe you want to try to use one of the shade trees, or if you have all numeric data, that's pretty straight, maybe you want to use a regression model. But since we had mixed data, it was a reasonable choice. You know, I didn't know it was right, and maybe there's something better to use, but it's a starting place. And so a lot of the process is to iterate through.
So you usually try out other kind of math, like I'm not just talking about decision trees or random forest, like something entirely different, like regressions.
Yep.
Because regressions still can handle it categorical and very as well.
Yeah, I mean, there's all kinds of algorithms to use, and certainly you want to look at them and try them. Maybe you want to do support vector machines or gradient boosting. Maybe you want to do just some other ensemble methods.
And so then you just base on it, and then you base your decisions on like whether the sensitivity on picking the algorithms, or
And there's a whole lot of evaluation metrics too. And so really you want to just think about what problem it is that you have, and you kind of decide on an evaluation metric early on, and say, well, we're going to use this metric. We're going to just evaluate our model based off of how much stuff it gets wrong. But you can absolutely use different metrics. Like I said, the Kaggle competition often use the root mean logarithmic square error, and so that's saying, how far away are you? Yeah, so there's a lot of different stuff. So a lot of it's covered in the recommended reading. That one is doing data science, and they go through some of that and some more specific scenarios and how to evaluate it. And feel free to email me or send Twitter questions to my Twitter account too.
Well, you mentioned you use 500 trees, 500.
That's the default parameter.
Or 1,000. But I'm wondering how that would affect if you have your data is huge. I mean, like your training instance are like more than 10,000, 20,000 instances, and you have more than 25 variables.
Oh,
How's that?
so we have random lumberjack for a reason, because I certainly push the limits of our hardware and what this algorithm can handle. And so running stuff in parallel is important. You're going to run into a lot of memory constraints and stuff. But no, something that size that'll handle just fine. You're going to run into probably memory problems on your computer or server first, or you're going to run out into limitations with your core, your processing units. And so when you start spreading that out, maybe onto 10 cores, then you're going to get memory problems. You give it more memory, then you can spread it out a little bit farther. And so,
Well, but sometimes if you go a little lower than that, you can fit it in that hardware, and you can get better results if you go more than.
random forest is
I have
ridiculously
experience.
parallel.
Like
What's that?
if you go lower, sometimes you find the right number. It handles that, but the results are not really that good. I mean, maybe you can get 80%, but not 95%. So, I'm saying, is there like a limit where your data should be like more than certain dimensions?
Not that I've found. I mean, you don't want to have more than 32 factor levels. So if you do, you're going to need to start binning that or clustering it somehow. So you're gonna run into limitations because of your data, probably before you're gonna, I mean, it's a good algorithm, like it splits out, so you can just say, run 10 trees here, run 10 trees here, and put them together. If you're trying to run it all in one core, then you're gonna hit limitations depending on the hardware that you have.
So it's the only problem is the limitations of the hardware, so it's not the actual algorithm would have optimal.
So in the R
more
implementation, which
nodes,
does
more
the code to the original Fortran, written by Leo Bryson. But there's different implementations around the forest that don't work as well. So this specific algorithm works very well to spread out and parallelize.
And if you use the carrot package, actually it's a bit easier to do a lot of parallelizing. A lot of that stuff is, it's just a little more natural. So you can try different models and parallelize them all, using the same code and stuff, which is kind of nice. And I think I agree with it, that fundamentally, like, we've run pretty big random forests on pretty darn big data sets. And if you have a lot of memory on the machine, then it's fine. It's not a fundamental problem in the model. You just need 100 gigabytes of RAM or something.
I'm supervising the more trees and
If I mean, in R, that's a limitation of R a little bit, right? Is that it works in memory, right? So then you can just use Python. But no, I mean, you can get really far. You can get really big if you have a lot of memory.
So, trying to predict the weather is tricky business because it's a high causal density environment. But we've gotten a whole lot better in the last 10 years. There's been significant improvement in the predictions. But for example, if you were to use data from yesterday to try to predict the weather today, you would have better accuracy than if you used the data from last week, correct?
Correct.
So, for example, how do you factor that in terms of the time series of the data?
Well, so you look at seasonality and patterns, and so you're not going to build a model off of just last week or this month. You're going to look at data over time. So you're going to kind of look back. You're going to look forward, and you're also going to try to look at the patterns that might have existed a year ago, or just patterns in general.
And for example, I'm trying to predict the weather next Sunday because I know a certain quarterback doesn't play well if it's 30 degrees or lower, right? So that's valuable information to me.
Also, you can build your model today.
But if I use today's data to try to predict the weather on Sunday, it's probably not going to be that accurate. Or it may be. I mean, it's hit or miss.
It's a matter of discovery, isn't it?
Well, you can build your model.
Part of your variable selection, right? So you would actually put that in as part of your variable selection, right? Yeah. Start to think, put it in the season.
Yeah, I mean, you could build your model today and then feed it new data on Saturday.
I think I feel like also weather forecast is just stochastic modeling, like it's a classic example of stochastic modeling, because the data, the weather tomorrow depends on today's date weather as well. And also all the other like factors, like wind conditions and air pressure. And tomorrow's weather also depending on the air pressure and all those. So I thought that's why I think it goes back to my questions that it has like a better prediction because you factor in today, the days before and 2 days before and some of the previous days. This is more time series data, it's not just classification.
Yeah, you saw what I did. I said date. We're not putting it to the model.
There's actually a whole chapter of this, if anybody's read Nate Silver's book, The Signal and the Noise, he actually talks about it. There's like a whole chapter dedicated to weather forecasting and the advances that they've made. And not just approaching it with a probabilistic approach, but just using supercomputers to actually simulate the atmosphere and how much better they've been able to improve. You might not approach it with a probability, from a probability perspective. Looking at today's data, you may just have to model it to get better predictions. There's a lot of, if you're interested, I mean, the book is pretty good, it's pretty long, I mean, I'm not an expert on it, I've only gone through it once, so, I just point you in the direction to take a look at it. If you want to know more about how to better predict whether or not Peyton Manning will be able to throw the ball next Sunday.
Yeah, we want to know.
But isn't it a matter of discovery? If I wasn't sure, I'd say, let's feed it the weather for the last 30 days each day and see what does predict the weather tomorrow. Right? I mean, that might be one of the models I try and see if I get better results, as opposed to feeding it just today's weather to see what tomorrow's is like. And whichever works better is what I use.
Thank you.
Thanks.
Please support our sponsor. Join us at Old Chicago. Thank you very much.